everyone, what's up? Welcome back to your favorite channel, Byju's Class 8, 9 and 10. How are you? I hope you're doing great, everybody's safe. Yes? Amazing. Hi Fenil, hi Lakshmi, hi Manjot, hey Christina. It's so good to have you back. Yes, hi Deepthi. So Deepak is asking, do you remember me? Yes, of course I do. Hi Divya. Hi Kanishk. I remember most of you. You people have been really attentive. You people have been really regular for all the classes. Right? Hey Ojal, hey Ananya. Hi Gungun. Yes, finally we are having the class after such a long time. And hey, this reminds me of something. So today it's going to be a special class. Why? Why am I saying that? What is going to be so special about today's class? Come on, if you know it, you tell me in the comments section. So, over here, I can see your chat, I can see your comments. Let's see who knows what is going to be so special about today's class. Alright, you want some hint? Okay, there you go. That's your hint. One shot. What is it? You must have seen this in other subjects as well. A lot of you are writing about one shot. Great. So what exactly are we going to cover today? We usually used to meet on Wednesdays, right? Now we are meeting twice a week. We will be meeting on Tuesdays and Wednesdays. So what are we going to cover today? What do you think? Ananya says super review. Absolutely right. So we are going to cover periodic classification of elements in one shot. We are going to cover this entire chapter in one go. Yes. You really wanted us to come up with comprehensive classes, isn't it? Yes, so consider it done, and today it's going to be a power-packed class. Absolutely, Yasharth. Alright, but before we kickstart with today's session, you have to tell me if I'm perfectly audible and visible or not. Is this PPT working fine? Give me loads of thumbs up, give me some good smiley faces so that I know that we are settled, we are good to go. Alright, Deepak feels that this is a very tough chapter. So we'll do one thing, we'll make it easy for you. Papya is giving loads of thumbs up. Yasharth is also saying everything is working perfectly fine. Yes, power pack class. So let me see some power packed emoji over there. Let's see. Divya is also confirming that. Great. Alright. Hi Punjabi swag, I'm doing well, thank you. Hey Deepak, Divyansh feels this is the easiest chapter. Well, I hope by the end of this lecture, all of you are going to feel this way. Great. Alright. I can see some nice emojis coming my way, which means we are settled, we are good to go. So let's begin with today's class. Periodic classification of elements. Now, you see your term elements there, right? When we talk about elements, we know what elements are, right? In class 9, we've covered that. We know what elements are, and we know some of the very basic elements, common elements. So carbon is there. Entire life is carbon-based, right? We hear about oxygen, we hear about hydrogen, zinc, aluminium, magnesium, and I can go on and on and on. But hey, how many elements do you know that have been discovered till date? How many elements have been put into the periodic table? Let's see. Bhagya, Nikesh, Studio Dev, everybody is saying 118 elements. And you people are absolutely right. So, 118 elements have been discovered so far, out of which 94 are naturally occurring. So over here, we've given you some of the elements, right? Now, imagine that there's a class and I'm the class teacher and there are 30 kids in the class. It's very easy for me to know the property of these 30 kids. By property, I mean nature here. So I would know the name, I would know their nature, right? Sorted life. So that initially happened with elements also. Only 30 elements were being known. And to study those elements individually, it was quite easy. But now imagine that there's an entire school and there is no organization out there, okay? So in a class when I enter, I see somebody whose age is 5 years, somebody who's 10 years old, somebody who's 15 years old. And I am sure I'm going to go insane, right? I would not know what to teach. That is why Even when you go to school, you've got different grades. Grade 1 is there, grade 2, 3, 4, 5, 6, and so on. Now when a teacher enters class 7th, he or she knows what to teach. When the same teacher enters class 10th, and she would know what to teach in a detailed manner. So there is an organization, there's a systematic manner. Similarly, when elements are so high in number, 118, scientists started thinking, how can we have some kind of systematic manner over there? How can we organize them in a better manner? Can it be on the basis of chemical properties, maybe physical properties, maybe reactivity? So they started thinking, what is the best basis to classify elements so that everything becomes very convenient to study? Yes, absolutely. Convenience, yeah, we all want convenience, isn't it? So, based on this, we have four major classification. We have four major scientists who came up with their approach to classify elements. First was Dobereiner. So in 1817, he came up with law of triads. Then John Newlands in 1866 came up with Newlands law of octaves. Then Mendeleev in 1869 came up with Mendeleev's periodic table. And hey, I'll put a star over here. I'll tell you why. Then Henry Moseley in 1913 came up with modern periodic table. So this entire chapter is basically divided like this. Alright, great. So let's do one thing. Let's start with the first one, that is Dobereiner triad. And I'll keep giving you hints in between to remember all these things easily. So don't worry about that. Great, nice. Just waiting. I was also actually waiting for the session. Full energy, absolutely. Chalo, let's see what did Dobereiner actually say. He basically said that if the elements are going to be arranged in groups of 3, which he called as triads, then in that case, if we are arranging the elements in the increasing order of their atomic masses, he clearly stated that the mass of the middle one, over here, 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 these are the middle elements, right? So the mass of the middle one is going to be the average of the masses of other two. So I'll do one thing. I'll calculate for lithium, sodium and potassium, and you are going to calculate for, okay, you're going to calculate for chlorine, bromine and iodine. So 3 elements are there, that's why it's forming triad. Tri means 3. Easy to remember? Alright, so I'm calculating for lithium, sodium and potassium. So I've got 6.9 plus 39 by 2. So this actually comes out to be somewhere near 22.95, which is very near to mass of sodium, 23. Isn't it? Hey Bhagya, you're quite fast, great. Anybody else for calculating for bromine? Let's see. Tanushri is also calculated, nice. So, in case of chlorine, bromine, iodine, what do you have? You've got 35.5 plus 126.9 divided by 2. This will give you the mass of bromine based on this particular formula. Gungun, Shreya, all of you have calculated. Vaibhav, Nikesh, Christina, great. It comes out to be 81.2, which is very near to the mass of bromine, 79.9. Now, the easy way to remember that Dobereiner came up with triad. So, listen to the hint very carefully. How many letter E do you see in this term, Dobereiner? You see 1, 2, 3, right? 3, that's your hint. So, he came up with triads. Triads mean 3 elements being placed in one particular group. Now, whenever I talk about Dobereiner, you need to remember that we are talking about triads. Great. Yes, absolutely. So this 3E will help you remember that. Alright. So well done, Dobereiner. It was great that you've discovered triads, but there was a little drawback in this. Not all elements discovered at that time could be grouped in sets of averages. That means not all the known elements at that time could be placed in terms on the basis of triads, right? For example, you've got nitrogen, you've got phosphorus, you've got arsenic. Based on this, if you calculate the mass of phosphorus based on this formula. Let's see. 14 plus 74.9 divided by 2. What is it coming out to be? Nearing what number? Let's see. Let's see who's actually good. Oh, Bhagya has again answered it first. Great. Hey, Bhagya, you did not even let me complete and finish my sentence. Great. 44.45. All of you are very quick. That's awesome. It comes out to be somewhere near 44.45. And this number that you see over here, that is not equal to mass of phosphorus, right? So, clearly this law is not applicable over here. Moreover, he could discover only 3 trides. So, this is your tride number 1, lithium, sodium, potassium. This is your tride number 2, calcium, strontium, barium. And this is your tride number 3, chlorine, bromine, and iodine. It's going to be very easy for you to remember. 3 trides and 3 elements in each tride. So 3 is the key over here. Alright, thank you, Shreya. Yes, Ananya. So he was not able to make more trides. That is going to be the drawback of Dobereiner. Alright, so we are done with this one. Let's move on to the next one, that is Newland's law of octaves. You see a table out there, right? Now what exactly did Newland say? He said that I'm going to arrange all the elements in the increasing order of atomic masses. So the basis that he has chosen is atomic mass, and he arranged the elements in the increasing order of atomic mass. And then he said the properties of every 8th element were similar to the first element. Now all the music lovers out there will easily get to know this one. You've got sa, re, ga, ma, pa, dha, ni, and then sa is the 8th note, which is similar to the first one. Or maybe do, re, mi, fa, sol, la, ti, and do again is the 8th note similar to the first one. Similarly, he gave his law of octaves that every 8th element is going to be similar to the first one. Now, how are you going to remember this? Again, I'm going to give you a hint. Yes, absolutely. Okay. Let me give you the hint first, then I'm going to take this question up. How many letters are there in Newland's? You've got N-E-W-L-A-N-D-S. 8 letters. So, he came up with octaves. Oct means 8, right? So, this is how you'll remember that every 8th element is going to be similar to the first one. Yes? Great. Yes, Puneet, absolutely. 8 octaves. Now you're not going to get confused between Dobereiner and Newland, because I know that this is one basic silly mistake that we might do actually, and that is completely avoidable, right? Yes, Vartika. Absolutely, Vaibhav, correct. So give me a thumbs up if now you're not going to get confused between Dobereiner and Newland. So Dobereiner came up with triads, Newland came up with law of octaves. Alright. Now, what you see over here is kind of an achievement of Newland, but having said that, there are drawbacks of Newland's law of octaves as well. First of all, this law was applicable only till calcium. So after calcium, beyond calcium, this law was not true. This was the first major drawback of his law of octaves. Moreover, the second drawback is, in order to fit elements, he placed unlike elements together under the same note, as you can see over here. Well, that's a big no-no, isn't it? So again, this one is a major drawback of Newland's law of octaves. Then there's another drawback. You see cobalt and nickel over here. Now, cobalt and nickel have different properties if you compare them with fluorine, chlorine, bromine, right? They're not the same, but it's been placed under the same family. Well, again, this is not something that is correct. So this is again a drawback. And moreover, cobalt and nickel, they are very much similar to iron. Where is iron and where is cobalt and nickel? So far away, isn't it? So similar elements were being placed in different families. So again, this is nothing but a drawback of Newland's law of octaves. Alright, there's another one. Novel gases that were being discovered later, they made the law irrelevant. So these are the novel gases. Whenever they were being discovered, this law again was not held true. So these are the major drawbacks of Newland's law of octaves. Now, we know about Dobereiner triads, we know about Newland's law of octaves. Then Mendeleev came up with his version of periodic table. Now just have a look over here. If you'll notice carefully, for Mendeleev we are writing the term periodic table. That means Mendeleev did some great work, right? बहुत कुछ major achievement उनकी होगी, that now we are slowly moving towards the periodic table, isn't it? Let's see what did he came up with. All right. Now in 1869, Mendeleev came up with his own version of periodic table. At that time, 63 elements were being known. So what he did, he took 63 cards. Okay, we all love playing with cards, right? And so did Mendeleev. He played chemistry and cards and mixed them together, right? So he took 63 cards, and on every card, he wrote the properties of elements. Then, you won't believe that he actually carried these cards wherever he went. If you Google about it, you'll know that he actually carried these cards everywhere that he went. Then he said that there's going to be a relationship. There's going to be a relation between atomic mass of the elements and their properties, physical properties and chemical properties. He tried to rearrange all those cards, and finally he came up with a basis. And how did he decide the basis? He said that all the elements that are there, they are going to react with some standard elements. Now, these standard elements he's taken to be hydrogen and oxygen. Okay, all the elements are out there, and those elements are made to react with hydrogen and oxygen. So these are the two standard elements that he has taken. Why did he take these two elements only? The first reason, that they are very reactive. And if they are very reactive, they are going to form compounds with most of the elements. Plus, they are found readily. So, let's see what did he observe when he did the same. Yes, absolutely. Yes, yes. Yes, Fennel. True. Sia says hydrides and oxides. Alright. Sia is actually right. Formula of hydride. So you've got hydride of X over here, you've got hydride of Y over here. Then you've got oxides over here, oxide of X and oxide of Y. And this was the basis of his classification. And there you go. Based on this, he could actually make a good table out there, right? Quite some work, isn't it? Now, let's just zoom a bit over here and see. When we magnify this, just have a look over here. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. When you look at the masses are increasing, right? So, increasing atomic masses are there. Now, he came up with his law that properties of elements are the periodic function of their atomic masses. And this very much holds true. Alright, now over here. We have to understand this table, right? You see vertical columns out there. What are these vertical columns? These vertical columns are known as groups. And how many groups are there? Come on, tell me. How many groups do you see? You just have to read the table properly. And this is an easy peasy question. Hey, right, absolutely. 8 groups are there. Then you also see some rows, horizontal rows, right? And these rows are called periods. How many periods are visible over here? Well, I see some of you write 18 groups. See, we will come to modern periodic table also. As of now, we are discussing Mendeleev's periodic table. Mendeleev ने इतना अच्छा काम किया, थोड़ा सा we need to discuss that too, right? Alright, absolutely right. Divya says 6, Aishwarya says 6, and so there are 6 periods. Great. What else is there in the table? We see oxides and hydrides. Hey, you remember? We chose oxygen and hydrogen as the standard element with which every other element was reacting. So, of course, they ought to be there over here, right? Now, look closely. What is being given to you? These are the general formula. So, for oxides, suppose I pick up group 1. The general formula is R2O. Now, suppose I want to see what is it going to be in case of lithium? It's going to be Li2O. For sodium, Na2O. Simple, isn't it? Based on the general formula, we can easily decide what chemical formula various elements are going to have. Now for hydrides, let me pick up group 4. Let's see the general formula. It's RH4. Suppose I talk about carbon, so it's going to be CH4. silicon, SiH4. So R is nothing but the element over here. Based on this, this is how his periodic table was being framed. Hey, good to know that you're finding the chapter easy. That is the whole purpose. Nice. Fenil is finding it very easy now. Riya is also finding it easy. Great. Alright. Now Mendeleev, as I said, इतनी अच्छी achievements Mendeleev ने करी है. First is this systematic table that you see over here. So systematic that basically provided a very organized way of studying elements. Right. Now, over here, what do you see? Cobalt and nickel, and look at their masses. Over here, the sequence is slightly inverted, isn't it? For tellurium and iodine, again the sequence is inverted so that the elements basically with similar properties could be kept together. So he kind of made little changes here and there. We are going to come back to this. This is a very important point. We will be back on this point. As of now, let's take the first achievement to be a very systematic study of the elements which were known at that time. Yes. Okay, yeah, I'm coming to that one only. Okay, let's explore his table a bit more now. Please go ahead. Okay, I see you writing about Eka. Okay, so let's go to that part only. Over here, what do we see? We see some vacant places, right? Now, I'm calling these vacant places as defects. But Mendeleev said, hey, don't call these as defects. They are very much gaps. And he boldly predicted the elements that were not discovered at that time, that were yet to be discovered. And he said that whenever these elements will be discovered, boss, they are going to fix in these gaps perfectly. And that actually came out to be true later. So, at that time, he named these elements as Eka boron, Eka aluminium, and Eka silicon. Now, what is this term? This is a Sanskrit numerical which basically means first or one. So, when I say Eka silicon, let me take this example. Eka silicon basically means, Eka means first, right? So, first silicon would come and just below silicon, this new element would be there. Yes. Yes, Nikesh, true. Divyansh, because this is not the modern periodic table, this is the Mendeleev's version of periodic table, which is not the ultimate one. That is why you might find some of the elements placed haywire. Now, later, when these elements were being discovered, they were named as scandium, gallium, and germanium. And as Mendeleev predicted, and I should say boldly predicted basically, properties of Eka silicon were similar to germanium, Eka aluminium was similar to gallium, Eka boron was similar to scandium. So this was another big achievement that he did, that he predicted some elements even before they were being discovered, right? Great. Absolutely true, Nitila. All right. True, true. Chalo, let's move on. Now, noble gases were being discovered later, right? Because as the name suggests, they're noble, they're inert, they're unreactive. Plus, they were basically found in low concentration. So, they were being discovered quite late. But, hey, whenever they were being discovered, have a look over here. They are fitting in this table perfectly fine without disturbing other elements. So that is another achievement. So group 0 is being introduced over here. Hey, Rudra got it. Great. Yes, Aishwarya, position of noble gases. It did not disturb Mendeleev's table, which is another achievement. Great. Now your task is to find out when exactly were these noble gases being found. All right. Abu Tahir has a very interesting doubt. Ma'am, how did Mendeleev know about Sanskrit? Let's see who's going to answer his doubt over here. All right. Now, He did a great job, but there were limitations. There were limitations to, basically these three limitations were being seen in Mendeleev's periodic table. The first one is no fixed position was given to hydrogen. Now hydrogen was kind of resembling alkali metals also, and it was resembling non-metals also. Just like alkali metals, it was easily combining with halogens, oxygens, sulfur and forming compounds with similar chemical formulae. But just like halogens, which are non-metals, right, it was existing in diatomic form. Now Mendeleev was confused where to put it exactly. So this position of hydrogen was basically a controversial one. Moreover, isotopes whenever they were being discovered, they violated Mendeleev's law. Go back to basics, recall what are isotopes. They have the same atomic number but different masses. Now suppose I talk about carbon 12 and carbon 14, right? I'm talking about two isotopes of carbon. According to Mendeleev's law, they're going to be placed one next to the other, right? But they are the atoms of the same element, isn't it? They need to be put together. So this is another drawback of Mendeleev's periodic table. The third one is that the mass is not regular. It's not completely in the ascending order. So you remember he gave a systematic study, but I said I'm going to come back to this point, and somebody was writing, how is this an achievement then? Achievement is that he could place it systematically, but yes, since it is not increasing in the ascending order, it's not increasing regularly. Both these things are the limitations of Mendeleev's classification. Great. Alright, thank you Karina. Let's move on. So, this is done, and now the main part. Henry Moseley came up with modern periodic table. He said that, okay, Dobereiner, Newland, Mendeleev, they've been using atomic mass as the basis. He said, I'm going to change the basis only. सब कुछ बदल देते हैं, and then let's see what happens. He said that I'm going to bring up a modern periodic law which states that properties of elements are a periodic function of atomic number. So, till now, whatever we were studying, the basis was mass, somewhere or the other, right? He said, mass से तो काम नहीं चलेगा, atomic number try करते हैं. What exactly is atomic number? Atomic number is number of protons. Now, why is this a more fundamental property? Well, let's see. When we move from one element to the next one, atomic number increases by a constant unit of 1. So if you're going to see the modern periodic table, it's 1, 2, 3, 4, 5, 6 and so on, right? In a way, the difference remains the same. That is 1. The increment is by 1 unit. So obviously this is a more fundamental property. And there you go. Finally, we've arrived at the modern periodic table, and over here you see 18 groups. 18 groups are there, 18 columns, right? 18 vertical columns, and you see 7 periods. And please notice the atomic number. It's increasing in the right. Okay, Narendra says arithmetic progression, which I think Narendra is absolutely right. Narendra Kumar is saying they're forming AP. Yeah, they are. They are very much forming AP. And what is the difference? What is D over here? It's 1, right? And it's so cool you people are mixing maths and making it an integrated study with chemistry. Great. Amazing. Yes, it is forming an AP. With the difference being 1. Alright. Absolutely. Hey, Puneet is asking who knows all the elements. Well, let's see who knows. Okay. Alright, chalo. Now there are major trends that we need to cover when it comes to periodic table, and these are the 3 trends that we will be talking about. Let's start with the first one, that is valency. Now, valency. Have a look over here. 1, 2, 3, 4, 3, 2, 1, 0. Let me do one thing. Let me write down valence electron over here. 1, 2, 3, 4, 5, 6, 7, 8. So, for the groups out there, I have written the valence electron. If the valence electron is 1, valency is going to be 1. If the valence electron is 2, valency is going to be 2. If it is 3, it's going to be 3. If it's 4, it's going to be 4. Till here, very sorted. Now, how can we calculate for the rest? For the rest, you're going to apply a very simple formula. 8 minus valence electrons. That is going to give you the valency. So for group 15 over here, it's going to be 8 minus 5, that is 3. For group 16, it's going to be 8 minus 6, that is 2. Similarly, 8 minus 7, 1, 8 minus 8, 0. So noble gases, obviously they don't have any tendency to react, right? They are very much stable. So what is happening to valency? It is increasing till 4 and then it is decreasing. Easy peasy. Great. Good, Yasharth. High five, Kaushal. Alright, now look at the groups 1. Can I say that the valence electrons are remaining same? When I go down the group, valence electron, I'm picking up random groups. So for group 13, it's 3. For group 17, it's 7. Valence electron is remaining same. So if valence electron is remaining same, valency is also going to remain same. Alright, so there you go, that's the trend. When we talk about valency, it first increases and then it decreases. And when we talk about valency down the group, so this is valency across a period, left to right. Now, down the group, it's going to remain same. And why is it remaining same? Because valence electrons down the group, they remain same. Alright. Great. Chalo. Let's move on to the next trend, that is atomic size. Alright. Atomic size में ना confuse नहीं होना. It's nothing but the radius of an atom. You know what radius is, right? You've been integrating math, so I assume now you know what radius is. So the distance between the center of the nucleus and outermost shell, that is nothing but your atomic size. Now, there are two terms over here. Nuclear charge and effective nuclear charge. This is one topic where you can get confused, where you might get confused. So I would be discussing this. I'll take a minute over here and discuss this one. What is nuclear charge? You know what? You know there's a nucleus, you know neutrons are there, you know protons are there. Neutrons are neutral, protons are positively charged. So because of protons, nucleus becomes positively charged. Total positive charge present in the nucleus, that is nothing but your nuclear charge. But hey, there's another term which is effective nuclear charge. It is the total nuclear charge experienced by valence electrons, and they are saying that nuclear charge is going to be greater than or equal to effective nuclear charge. How do we understand this? Imagine I'm standing in an auditorium, okay, and I'm shouting, "Good morning, class." Now there are students who are sitting in the first row, and then there are students who are sitting maybe in the 50th row. For me, I'm using the same volume, I'm using the same pitch, same tone, everything same. But the ones who are sitting closer in the initial rows, they are able to hear me properly as compared to the ones who are sitting at the back. This is nothing but actually the basis of effective nuclear charge. So as the shells keep increasing, effectively the attraction between the nucleus and the electron goes on decreasing, because now the new electron, valence electron, is moving further away from the nucleus. So now you should not get confused between nuclear charge and effective nuclear charge. Alright, now let's see what happens to the trend of atomic size when we go down the group. Well, I think you can figure that out now. When we talk about down the group, obviously atomic number is increasing, so there is an increase in the number of protons and electrons. Obviously, atomic number is increasing, number of protons and electrons are increasing. So in a way I can say nuclear charge is increasing. But hey, as we go down the group, what happens? Electrons are being added to a new shell. For example, lithium 2,1, sodium 281, potassium 2881. Valence electron is being added to the new shell. And when this happens, distance between outermost shell and nucleus is increasing. So there you go, effective nuclear charge is decreasing. If the effective nuclear charge is decreasing, attraction is going to decrease. Electrons will not be held that tightly. So atomic size is increasing. There's an inverse relation. If effective nuclear charge increases, size decreases. If effective nuclear charge decreases, size increasing. Irrespective, in this case, even if you see nuclear charge being increasing, okay? Yes, Nithala, extra shell. Yes, Aishwarya, absolutely right. Alright, Now let's see what happens to atomic size across the period. That means when we go from left to right. When you see over here, again, there is an increase in atomic numbers. So protons and electrons are being increasing, which results in the increase in nuclear charge. We've got 11, 12, 13, 14, 15, 16, 17, right? These are the atomic numbers, and these are the number of protons and electrons present in neutral atoms, right? Now, clearly, nuclear charge is increasing. Because proton number is increasing, electron number is also increasing. But hey, the increase in the proton number, the effect of this is way more as compared to the increase in electron number. Why? Because electrons now are being added to the same shell. Now, since they are being added to the same shell, effectively nuclear charge is increasing. Now, the electrons are being held tightly. The force of attraction is more. And if the force of attraction is more, what's going to happen to the atomic size? It's going to decrease. All of you have written the same thing, that across the period size decreases. It's great to know that you've understood the concept. Because if you've understood nuclear charge and effective nuclear charge, you can solve any question of periodic table. Great. Alright. Chalo. So this was all about atomic size. Let's move on to metallic and non-metallic character now. This is a very easy and interesting trend, okay? First of all, you should know what exactly is metallic character. The tendency to lose electron is basically telling you about metallic character. Obviously, metals generally are electropositive in nature, and they want to lose electrons during bonding, right? So you've got a metal after losing electron, which has a negative charge. So if a metal is losing electron with a negative charge, it's going to become positively charged, right? And this tendency is nothing but metallic character. Now, more the tendency to lose electron, more is going to be the metallic character. Alright, now let's come back to the trend and see. First of all, down the group, we are discussing down the group over here. What is happening over here? Effective nuclear charge is decreasing, right? As we go down the group, shells are being added. If shells are being added, effective nuclear charge is decreasing. If the force of attraction is decreasing, the tendency to lose electron will be more. It's going to be easy for the electron to be coming out of this force of attraction, to leave the atom, right? So metallic character increases down the group. Now, let's see what happens across the period from left to right. When we talk about across the period, effective nuclear charge is increasing because now the electrons are being added to the same shell, right? So the tendency to lose electron decreases because of greater force of attraction. Nucleus चाहता ही नहीं अब electron जाए छोड़ के. तो क्या होगा उससे? Metallic character would decrease across the period. So over here, this is your main trend. Now you know about metallic character, you would definitely know about non-metallic character, right? It's just the opposite. Non-metals have a tendency to accept electrons and form negative ions. Electron has a negative charge. So if you have a non-metal which is accepting a negatively charged species, which is an electron, negative particle, right? Electron is a negative particle. Once it is being accepted, what do you get? Negative ions are being formed. Now, more the tendency to accept the electrons, more is going to be your non-metallic character. Now, to understand this is another very important concept of electronegativity. The name is self-explanatory, I know. And you people are smart enough to understand it also. It's basically the tendency of an atom to attract the shared pair of electrons towards itself. So, obviously, generally non-metals tend to be electronegative. They want to get the electron. They want to attract the electron. Electronegativity increases with decrease in metallic character, right? So, this is another very important point. Sometimes they ask you in terms of electronegativity. Sometimes in the exam, they can ask you questions based on non-metallic character. So, you should know that they are on the same line. Hey Puneet, no Menti today. But we are going to have a good practice session. Don't you worry about it. Alright. Now let's see about the trend of non-metallic character. Let's see. Down the group non-metallic character, basically, I can call it electronegativity, it decreases. So since electronegativity is decreasing, in a way non-metallic character is decreasing. They're interlinked, right? You can easily make that out. Alright, why is this happening? As we go down the group, electrons are moving away from the nucleus. So the force of attraction between the nucleus and the electron is decreasing. How can it attract the shared pair of electrons towards itself? So electronegativity is decreasing, and if it's not gaining electrons, so non-metallic character is also decreasing. Across a period from left to right, what happens? Let's see. Electronegativity increases and therefore non-metallic character increases across a period. Now, I'll give you a very easy hint to remember this. When you look at the periodic table on the left side, what do you see? You see metals. On the right side, you see non-metals. So obviously, as you're going to move from left to right, metallic nature will decrease and non-metallic nature will increase. So remember this hint, and you don't need to mug up anything then. Great. Alright, this nature of oxides also something that you can easily predict. We know that metals form basic oxides. So metallic oxides are basic in nature and non-metallic oxides are acidic in nature. Based on this, what do you think what's going to happen to the basic nature of oxides? What's going to happen to the acidic nature of oxides across a period? If you know it, write it in the comment section. Let's see. Let's see if you've understood about metallic and non-metallic character. Okay. Many of you are giving me thumbs up that you've understood. Now give me the answer. Great. Yes, absolutely. So, nature of oxides, say suppose I talk about basic oxides. Basic oxides across a period from left to right is decreasing. As Dev is saying, because metallic character is decreasing. Great. Now, acidic nature of oxide increases. Why is it increasing? Because non-metallic character increases across a period. Alright. What happens down the group? Well, there's no change, no much change in the nature of oxides. Yes, absolutely true. Great. Now, let's quickly recall all these trends. First of all, we studied about valency. So valency first increases, reaches the maximum of 4 and then decreases across a period. And down the group, it remains same because valence electron would remain same down the group. Then we studied about atomic radius, which decreases across a period. Why? Because effective nuclear charge is increasing. But down the group, your atomic radius or atomic size is increasing because now the electrons are being added to the new shell. Metallic character across a period decreases, non-metallic character increases. You see the metals out there, right? Left side metals, you see the non-metals over here. So, when you see the non-metals over here, you know they are on the right side, metals are on the left side. Left to right, metallic character is decreasing and non-metallic character is increasing. Down the group, what happens? It's the reverse. Metallic character increases because it is easier to lose the electron. And that's what metals want to do, right? And non-metallic character decreases. Why? Because it is difficult to attract the electron, right? So, non-metallic character is decreasing. Now, this modern periodic table has been really great so far, but it also has some drawbacks. First of all, the position of hydrogen is still uncertain. Okay, why? Because it cannot be placed in group 1, it cannot be placed in group 17, or maybe it can be placed in both, right? So this is still controversial. Maybe in some of the periodic tables, you will see that they have just placed it in the middle. कि confusion ही खत्म हो जाए कि कहाँ करना है, group 1 या group 17. Moreover, lanthanides and actinides have not been placed in the main body of the periodic table. They are being placed at the bottom. How many of you have noticed this? That they've been placed at the bottom. Otherwise, the table would become so elongated and it might disturb other elements also, right? Yes. UPSC Gold GK. Great. Nikesh is saying who's going to be the next scientist then? Well, any one of you. whoever is going to figure out where hydrogen needs to be placed. अब decide कर लो. Great, Fenil. So Fenil noticed, Charvi noticed, so many of you noticed that they are being placed at the bottom, not in the main body of the periodic table. Now, we've covered the chapter, right? We've covered the chapter in one go. Based on this, we've got a question for you, which is going to be your homework. So right up after this class, take some break and then solve this question. And what are you going to do? Once you know the answer, of course, after this class, once you know the answer, you're going to come back to this link and post your answer in the chat box. So right before the next class, we'll discuss this one. Okay? So give me a thumbs up if you will be sincere and you will do the homework. Great. All right. As I keep telling you, we've got you covered. We've got amazing classes lined up for you people every Monday to Friday. All you need to do is like, share and subscribe, and don't forget to tune in. Bilkul. Absolutely. You're welcome, Aishwarya. Alright. Now, the next session is also going to be special. So today's session was special. Next session is going to be extra special because we are going to solve critical questions together. When are we going to do this? February 2. That is tomorrow, guys. Wednesday at 6 p.m. So we'll solve questions based on this chapter. So you've got two homework basically. One is the question that you've just saw. Second one is to revise this entire chapter so that we have a great practice session tomorrow. Alright, for the ones who've joined us for the first time, there's a link being given to you in the description box. And go to that link, take a free trial class, and I'm sure you're going to like it. Yes, Ishwar, it's going to be tomorrow. You're welcome, Manoj. Yashat, Narendra, all of you are saying you're going to do the homework. Great. So after doing the homework, you're going to come back to this link. You're going to paste, you're going to type your answer. That's how I'll get to know that you've actually done the homework, right? Great. Yes, even I'm excited for tomorrow's practice session. All right. Okay, great. Chalo, we are done with today's class, but I'll see you really soon. I'll see you in tomorrow's class. Until then, keep practicing, keep learning, and take care.